previous? Okay, then let's continue where we left off. So 7, 8, and 9, which are on this page, they all involve this graph. And the important thing about this problem is that for each of these individual problems, we actually have a slight difference in how we're interpreting this graph. So for 7, we consider this as the graph of just a function v. For 8, we consider it as the first derivative. And then for 9, we consider it as the second derivative. So each time there's a bit of a context switch in terms of like what this problem actually, what this graph actually is. We have to reinterpret it, and then from there figure out like what these words of like increasing, decreasing, min, max, concave up, concave down, and inflection points, what all of those things mean as based on what this graph is actually depicting. So I do remember like previously when I did this some other semester, there was a bit of confusion with one of these things. But yeah, if you think through like the definitions carefully, and you should try to do that for yourself to make sure that you can actually like reproduce the thinking process. But yeah, if you can do that, then you should be this should be pretty straightforward because it is basically just reading information off the graph. It's just there's a little bit of reasoning about it as well. Okay. Right. So let's see, 7. So this is just the function b in this case. And increasing means that the derivative is positive, decreasing means the derivative is negative. But also we can just like read it off from the graph visually since this is just the function v of x. And so that means increasing should be from minus infinity up to 1. Decreasing should be from 1 to infinity. Local max, you can just visually see that that's at the x coordinate only. So maybe I'll just say x is equal to 1. And then there's no local mins here. If we kind of pretend that the graph is a parabola that extends down infinitely, then there's no local min. Okay, concave up, that turns out to be nowhere. Maybe I'll say none. And concave down, that's everywhere. So minus infinity to infinity. Right, since the whole thing is like it's facing downward, it's opening downward, that's concave down. And then inflection point, well, inflection point by definition requires that you're transitioning from a concave up to a concave down or vice versa. So here there is no inflection point because there's no change in concavity. Okay. Number 8. So now we think of this graph as being the depicting the first derivative. Okay. So this is where we need to start thinking of just a little bit. So increasing means that the derivative is positive. Decreasing means the derivative is negative. Okay. And if we're viewing this graph as being the derivative, then it's increasing when the y value is positive. And so that means that this increasing is going to be from -1 up to, oh, not 1, but 3, up to 3. And decreasing means that the derivative is negative, which means the graph is negative. So that's from minus infinity up to -1 and from 3 to infinity. Okay. Local min and max, right? So that this is about the transition points, right? You normally say like that those things happen when the derivative at locations where the derivative is equal to 0. So that's going to be at the -1 and at the 3. And then whether it's a local min or max depends on if you're transitioning from plus to minus or minus to plus, like which particular order. So this one being a minus to a plus means that this is a local min. And so we can say, where's my cursor? X equals -1, it'll be a local min. And then x equals 3 going from plus to minus is increasing to decreasing, so that's a max. So x equals 3 is a local max. Right. Now concave up and concave down. So Well, concavity is going to be the second derivative, and concave up means that the second derivative is positive. Concave down means the second derivative is negative. So this graph, right now, we're thinking of this as being derivative. Um, and so we need to take another derivative on top of that in order to determine, like, yeah, whether it's concave up or down. So we can see that the derivative is going to be positive from minus infinity to 1. That's going to correspond to concave up. So concave up minus infinity to 1, and then concave down is going to be from 1 to infinity. Right. And the derivative is equal to 0 at x equals 1. So that's going to be the inflection point. Right. All right. Any questions so far? No? Everyone's fine? Okay. Right. Then for 9, we have the second derivative. Okay. So now we view this function as depicting the second derivative. And here we just have 2 parts, concave up and down, and inflection. Okay, so, well, concave up, concave down, there are statements about the second derivative being positive or negative. If we're viewing this graph as the second derivative now, then being concave up just means that we're positive, that our function is positive. So that's going to be from this minus 1 to 3. So we have minus 1, 2, 3, and concave down is the complement, it's everything else. So minus 1 to, or minus infinity to minus 1, union 3 to infinity. You can check that that is indeed where the function is negative. Okay, and then inflection points are when concavity changes. So that means that you have a change in sign happening for the second derivative. And that's actually at the places where this graph is equal to 0, at the minus 1 and at 3. So we can just put that down, x equals minus 1 and 3. So that's it for this page. And then this last problem, wow, today's going to be short. So this last problem is pretty much going through the process of something called curve sketching. So I think usually this type of problem shows up on the exam. So the process of curve sketching is just sort of something that you need to do. But usually we give you a rational function, and we actually give you the derivatives, and it's just that you have to pull the information from those the derivatives. Since taking the derivative can be a little bit more complicated for the rational function, since that involves quotient rule. Here, this is just a polynomial, so it's kind of easier to take the derivative. But so just as a recap of what the whole curve sketching process is, the idea is that you are gathering all of the data that you can from the function. So usually what we do is we find the roots, we find the intercepts, the x and y intercepts, we find the asymptotes, if there are any, vertical and horizontal. And then we also find the information from the derivatives, the increasing, decreasing information, the local mins and maxes, the concavity, the points of inflection. We take all of that data and we use that to build a sketch of the function. That's why we call it curve sketching. And the reason that this method works is because back before calculators existed, you would kind of need to do something like this in order to get a rough idea of how a function looked like. So this is actually a very applicable thing back before calculators existed. It's kind of surprising just how much we were able to sketch without calculators. Yeah, but you see more of that when you like look at really complicated things that are way beyond the scope of the class. But here we just have this polynomial, which is actually easy to graph. But yeah, okay, so let's go ahead and do all the parts. Okay, so critical numbers. So that's just setting the derivative equal to 0 and solving. Okay, so I don't want to do product rule. Instead, what I'm gonna do is I'm gonna rewrite this just to make it nicer to work with. So I'm gonna distribute, I'm gonna get x cubed minus 6x squared. Now I can just take a derivative very easily. Minus 12x, and we would set this guy equal to 0. And now we would factor out a 3x. So we get an x minus 4. And so put implies. So x is equal to 0 and 4. Those are my critical points or critical numbers. Okay, well, then part B is asking about the increasing, decreasing information. So that just means we use the first derivative, draw a number line for the first derivative, plotting the values and testing the intervals in some way, or filling out the sign chart. And if you do that, you're going to get plus minus plus. I'm just looking at this factored form of w prime, and I'm noticing like that both of these are raised to the first power. So we know that we're going to flip in sign when we go over the 4 and go over the 0. So that's the information. And now we just interpret this in words. So that means increasing is going to happen from minus infinity to 0, and also from 4 to infinity. Make that look a little bit nicer, maybe. And decreasing is going to be from 0 to 4. All right. Next, we want to figure out concavity. So that means we need to take another derivative. Okay, so w double prime. So I'm going to look back on this first derivative, this one particularly, because that's easier to take the derivative of. And so then we just calculate that. So that's going to be a 6x minus 12. Then to do the sign chart for w for the second derivative, what would make sense is to actually find like when is this equal to 0? Find the tick marks and then test the intervals. So this is going to give me 6x minus 2 is equal to 0. So then x is equal to 2. And so then w double prime, we have a tick mark at 2, and just we can easily see that that's plus and that's minus. And so concave up and concave down. I know that some people use this abbreviation, but I don't typically. I'll just use it this time because it's a bit faster. Yeah. And then the inflection point, well, we just found the inflection point by setting the second derivative equal to 0 and solving. Like that gave us the inflection point, more or less. There is one technicality actually with that. By definition, an inflection point needs to have that the concavity changes. So sometimes you might see that that you find places where the second derivative is equal to 0, but then like going from one side to another, you end up still having the same concavity, like it both being minus minus or plus plus. That actually, by definition, is not a point of inflection. For a point of inflection, you need the concavity to change. Yeah, I'm trying to remember if you see that normally or if that only happens by an asymptote. I think, no, I think you can. Yeah, I'm pretty sure you can make it so that it shows up naturally. But anyway, here we have x equals 2 as a point of inflection. Yeah, local mins and maxes, right. Well, that's going to be read off from the first derivative. So local min is going to be at x equals 4. And, oh, wait, I'm putting in the wrong spot. Local min is at x equals 4, yeah. And local max is at x equals 0. But now that we see we're supposed to actually sketch this, I'm now thinking that I need coordinates for these things, right? The inflection points, local mins and maxes, those are specific like points on my curve that I can figure out. And I kind of want them to be like landmarks for how I'm going to draw my function. So yeah, I should plug these into some version of this w function. So let's see, w of 2 is going to be 4 times minus 4, which is 16. Okay, so I have the point 2 comma 16 or negative 16 on my function. If I plug 0 Go 1 plug 0 and also 0 and 4. Well, they show up here, so okay, yeah. All right, so for 0, I'm gonna end up with 0, 0. For 4, I'm going to get 16 times -2. Maybe I'll just write that off to the side. W of 4 is equal to 16 times -2. So that's going to be -32. Right. Yeah. Yeah. Okay, so we have 3 coordinates, I think, that we can use. Well, there's one other coordinate, which is a root. We have another root for the function. But let's sketch this guy now. So 1, 2, 3, 4, 5, 6. Let's label 2, 3. And we know that at 4, we're at -32. And -32 is like the smallest value that we can see here. In fact, this is a local min. So I'm just going to put like a -32 here. And halfway, I'm going to put the -16. And so 4, -32 is about there. 0, 0 is another point we know about. And we also have 2, -16, so that's around here. But now this is a point of inflection, right? Yes. 0, 0 is a local max. So we kind of know the way that this curves around. So being a local max, it's got a curve like that. And 4, -32 being a local min means it's got a kind of curve like that. We also have, by looking at the function here, we can see that it has roots at 0 and at 6. So we know that it's going to have a point here as well. Okay, and now we can kind of just connect the dots, right? This guy is a cubic, so you can already kind of picture what that's supposed to look like. We've already put little placeholders to say what the local maxes are, and then we also need to just eyeball this guy and make sure that this coordinate is an inflection point where the concavity changes. So we kind of just sketch this as best we can and try to just connect the dots in a nice cubic fashion, I guess. So it's supposed to be a little bit more curvy, but that's as good as I can do on this device. Okay, any questions? You got a thumbs up. Well, if there are no questions, then I'll stop recording.